Hello, ladies and gentlemen, and welcome back. Hope you're all doing well, and hopefully you've enjoyed our 2015 COMC paper. We are going to have to say goodbye to it, because we are on the last question, question C4 here. And what have we got? Mr. Whitlock is playing a game with his math class to teach them about money. Okay, very nice. Mr. Whitlock's math class consists of n students, and there's at least 2 students, whom he has numbered 1 to n. Alright. Mr. Whitlock gives m sub I, which is greater than or equal to 0, so m sub I dollars to student I. So m1, m2, all the way up to mn. Alright, and he gives an integer amount of dollars. And we know that there is at least $1 in total. Okay, some students could get $0, but not all students will get $0. Some student will at least get $1. Okay, so we got the setup. Some money has been given out, some whole dollar amounts. Alright, we say a student is a giver if no other student has more money than they do. And we say a student is a receiver if no other student has less money. But they could have the same amount of money. Same as you can have, I guess, multiple givers. To play the game, there's a game? Oh yeah, they're playing a game to teach them about money. Okay. To play the game, each student who is a giver gives $1 to each student who is a receiver. It's possible for a student to have a negative amount of money after doing so. So, for example, if I had $1 and there were 2 people with $0, they'd be receivers, I'd be a giver. I'd give them each $1, but I don't have $2, so I drop down to negative $1. Okay, so I sort of owe the bank money, I guess. This process is repeated until all students have the same amount of money, or the students reach a distribution of money that they had previously reached. Okay. So, if I want to continue on this example, these 2 students would be givers, and each giver gives a receiver $1, so they would each give $1 back to this person who's now got the lowest money receiver, and they'd be back to 100. Because, of course, there's only $1 floating around. You can't divide that evenly amongst 3 people. Alright, nifty. Okay, I'm starting to understand the game. And hopefully a part here will ease me in a little bit more. So give values of n, m1, m2, all the way up to mn, for which the game ends with at least one student having a negative amount of money, and show that the game does indeed end this way. Okay. So in order to have it end with a negative amount of money, the students all can't have the same amount of money. So it's not ending because they have the same amount of money, it's ending because they've reached a distribution that they've had before. Okay. So we'll deal with that in a moment, but I always think it's a good idea to read the last question in its entirety, so the A, B, C, D parts all together, to really give us a sense of where this new money game is going. So we'll do that now. B, suppose there are n students. Determine the smallest possible value k sub n, so k depending on n, so that if the sum of all the money is at least kn, no player will ever have a negative amount of money. Interesting. And then in C, suppose we have just 5 students. Determine all quintuples with m1 less than or equal to, so we're going to have an order, it's an increasing order, for which the game ends with all students having the same amount of money. Okay, so there's 2 ways the game can end. We definitely want the same amount of money going on here. Okay. So I think with C, with C, we sort of have M1 is going to be a receiver, and M5 is definitely a giver, but if M1 and M2 are the same amount of money, then M2 is also a receiver. So I feel like there's going to be sort of scenarios, cases, like if these 2 are equal, but less than this, and less than this, and those 2 are equal, and that sort of a thing. And I guess there would be 16 scenarios, 16 different ways to place less thans or equals between those 5 values of money. Determine all quintuples. Do they want us to describe sort of a family, or I don't know. Let's get back to A. So, okay, we want the game to end with a negative amount of money. Well, I've already sort of briefly shown a way to do that. So we've got 1, 0, 0. We can get negative money that way. But then the game ends on the next step. So we definitely need to have... So that the previous step definitely has to be the giver has so much money. Or I guess there could be multiple givers. I don't know. I'm trying to think of just sort of the smallest, simplest example I can. So giver and then, a few receivers. But the number of receivers must be more than the, let's say, amount of money the amount the givers have. So I like this 1, 0, 0. What if I did something like 1, 0, 0, 0? So then $3 would be given out here. But then the people who were receivers become givers, and they just give it right back, and the game ends that way. Okay. So it looks like just with my very simple one giver, a few receivers, too many receivers, one might say, it just sort of bounces back and forth. We do get negative money. That's good, but we're ending where we don't want to end exactly. So, what could we do? Could we introduce maybe another person, like 2, 1... I guess we'll give 3 zeros. This person's still giving. And now I've got 4 givers, and they can each give back. They'll each give their dollars back, so it'll be 3, and then 0, 0, 0, 0. And then they'll give, and then the person with the 3 gives away 4 again, and it repeats. Okay, that's perfectly fine. We just need an example. And we've learned some things about having negative money. Okay, so I guess the thing that happened there is we had a person who later on became a giver or a receiver. That's I think what sort of worked out there. Because otherwise they'll just keep swapping positions. You got to have some sort of middle people. And I wouldn't have thought that they would necessarily affect things. But I guess as the money shifts around, they can slowly come into play and become givers and receivers in their own right. Okay, so, just briefly summarize that. So, n equals 5 with... They want the money distribution as well. Yeah. With 2, 1, 0, 0, 0 given out. Will do. I'll just very briefly explain. Just copying the same thing I wrote before. So it goes down to -1. Everyone gets $1. And then 3, and then back to -1, and then repeat position. Therefore ends. And we have -$1. Okay, that wasn't too bad. We found it sort of by playing around with it. Not bad at all. Okay, and now the B part. That was about no one getting negative money ever. So we want the smallest amount of money in terms of n so that no one will ever get a negative amount of money. No matter how we originally give the money out, provided no one starts with negative money, and they can't, because we always start with at least $0. Okay. So if I had n people, and we use something very similar to how I was playing around with this at the start. Imagine we just have one single giver, so suppose one giver and, I don't know, n-1 receivers. Okay? So basically what we're going to do is I'm going to try and give the giver, $D, and then give everyone else n-D. Or sorry, not n minus d, d minus $1. So d dollars, d minus 1, because this is the most we can give, or most everyone can have without getting additional givers. Now, who says you have to have one giver? I don't know. I'm just experimenting with it. So d dollars for the giver. So one person has that. And then d minus $1, and then n minus 1 people have that. Okay? So then the giver would give out its d dollar. Well, it would give out n minus 1 of the dollars. And then everyone would get an additional dollar added up. Now, if we ever have a situation like that, we don't want this to be negative. So we need d to be greater than or equal to to n minus 1. Right? Because if I start with one person who's got n minus 2 and n minus 1 people with n minus $3, then take away n minus 1 and you'll be left with negative $1, and then you'll have n minus 1 people with n minus $2. So if you have just one person with n minus 2 and the rest have as much as they possibly can, you can still get a negative amount. So they call it Kn. Kn has to be bigger than one person with n minus 1 plus everyone else having n minus 3. So this will be in terms of n minus 2, n squared minus 4n plus 3, so n squared minus 3n plus 1. Okay. Now, is there sort of a similar problem we could have with two givers? What if you had two givers? So two people with d dollars, and then give everyone else as much money as possible. So they'll have d minus $1. And then, well, I think if everyone is just givers or receivers, then it's just going to sort of hop back and forth. The money's just going to change hands a whole lot and not really settle down. Because the givers will give their money to the receivers, but then the receivers become givers, and they'll give it back to the new receivers who were the old givers. So we want each of these two guys to be left with negative 1. So we subtract n minus 2 times 2. And so they'll each have negative $1, so negative $2 in total. So I need d minus n minus 2 to be greater than greater than negative 1. So d needs to be greater than n minus 2 minus 1 n minus 3. So once again, Kn has to be greater than n minus 3 times 2 plus n minus 4 times n minus 2. So that'll be 2n minus 6 plus n squared minus 6n plus 8. That'll be n squared minus 4n plus 2. And since n is greater than or equal to 2, it's definitely less than this. So it seems like this is the value to beat. So I guess the question is, can k equals n squared minus 3n plus just one more, can that do the trick? Or do I need to look at it another way? You know, in part A, we needed this extra sort of additional person here. Do I have to start looking at non-givers, or non-receivers, non-givers, so sort of bystanders we might call them? Well, suppose this were the total amount of money. What could we say? This can be factored as well, can't it, to n minus 1 times n minus 2. I don't know if that necessarily helps, but it's just a thought I had. Well, so what was going on here? So can we? So suppose. What's the best way to say this? Consider a giver. What we want to do is show that every giver has at least R, or at least the number of receivers. Let's say let G equal the number of givers. R, the number of receivers. Maybe this is a good way to write it up. I'm not sure. I know that G plus R is less than or equal to N. We want to show every giver has at least R dollars. As they will lose R dollars in the first trade. Okay, how can I do that? That's the task. Well, maybe proof by contradiction, so suppose not. So then, I don't know, they were using M's, weren't they? Let M less than R equal the dollars that each giver has. Because they all have the same amount. Then everyone else has less than M dollars. Okay. So, what can we say? There is at least one giver and one receiver. Otherwise, the game would end before it begins. Okay? And then you'd have no negative money. So there's at least one giver, so G is at least one. So the total money is spelled with an E, is at most G times M plus N minus G times M minus 1. That's the most everyone else could have, and the givers all have M. I feel like this is too many variables. There's too much going on here, but we'll see. So that's GM plus NM minus GM minus N plus G. Those cancel out, so this is equal to NM minus n plus g. And we're saying that this must be less than r times n, or something to that effect. It's not really relating back to the original expression up here, so I feel like something is amiss. Maybe try a different argument. So I'll leave what I've written so far, but let's try a different approach, just because I feel like too many variables, and I'm not entirely sure what I'm trying to say here. So let's scrap it. We'll start again. So consider a giver. If they don't have n minus $1, they may have to give away too much money. I'm still not... How would that... Okay. So I'm not as convinced that this number here is exactly what I need. Especially because I'm not really starting my argument with it. I've shown that one less than that won't do. And so it seems sort of logical that this would be the number that might work, just because I've run out of other things. I can't think of another way to start things off. Well, hold on. So n squared minus 3n plus 2. There is at least one person with more than n minus $3. Why? Well, if n people had n minus $3, then that would be n squared minus 3n. But we have 2 more dollars. Of course, n squared minus 3n plus 1 also had an additional dollar. So with these 2 additional dollars, I guess we could have cases. So $2 additional dollars. Suppose one person has at least n minus $1. Then any giver has at least n minus $1, and so will not go into negatives when we trade. And once you've traded, you've got the same amount of money, it just shuffles around. And so this exact same argument will show that, all right, once the money's changed hands, once again there will be someone who has at least n minus $1, And so any giver in the second round of trading the money will also have at least n minus $1 and will still not go into negative. But, and so the $1 for n squared minus 3n plus 1 couldn't guarantee this. They would guarantee that someone has at least n minus $2. And those might, too many of those might be given away. So the second case, two people have at least n minus $2. Will this work, or do I need to maybe add a third dollar or something like that? So is there a way to... Okay, so if no one has at least n minus $1, then there are at least 2 givers. And so not more than n minus 1 or n minus 2 receivers. But my givers have exactly n minus $2, so that's going to be fine. Because they could at most give away all their n minus $2. If it's just these 2 people and their givers and all the other people are receivers, then my 2 givers will give away all their n minus $2, but they won't be in negatives. Alright, good. That took a little while. Basically, sort of all this. I mean, it was a decent try, but no, I wasn't really referencing the number that I thought might be the answer. So Kn equals n squared minus 3n plus 2 is the least amount of money, such that the conditions of B are satisfied. And we specifically know it's least because if you did n squared minus 3n plus 1, there's that distribution of one person getting n minus $1, having n minus $2, and the rest of the people having n minus $3, and that doesn't work out with no negatives. Alright. So C, this was about casework and 5 people, right? Alright, suppose n is 5, determine all quintuples for which the game ends with all students having the same amount of money. Okay. Well, I think rather trivially, we can at least know m1 plus m2 plus m3 plus m4 plus m5 must equal a multiple of 5. Total money must be divisible by 5 as a condition in order to divide it evenly. Now, just because we can divide the amount of money, we'll call them the sort of average m because they seem to like using m a whole lot. So in order to divide this up, you have to have a multiple of 5, but that doesn't mean that any sort of, well, doesn't necessarily mean that any arrangement of the money will always get to an equal distribution with this game. Maybe it will, and maybe we'll develop a proof for that, but it doesn't seem like that on the surface, just because, well, it seems like there's not enough sort of dynamic, there's not enough changing of hands of things, but, I'm willing to be wrong. In order to, must be divisible by 5 in order to divide evenly. And end with, they've been using tuples. Okay. So, that's a nice condition. Maybe it's the only thing, but maybe we have to add to it. Now we've got M1 has to be less than or equal to M2, less than or equal to M3. They've just told us this is how we're going to start it off. Okay. Now, when I think about my givers and receivers, there's only a set number of people here. But we could, for example, maybe M1 is a receiver, but maybe the top two people are givers. Now, how would you know that? Well, if they had an equal amount of money and it was greater than the third person, and M1 is definitely less than M2. Now, it doesn't actually matter the relationship between M2 and M3. What determines your givers and receivers are where these left and rightmost less than signs are. And I think those would be some interesting cases to look at. So I might say consider that the left and rightmost, or leftmost and rightmost, I think would technically be the right way to write this. In the inequality. Determine the number of givers and receivers. Okay. So, I guess how are we going to do cases is kind of tricky. So, if somehow there are no less than signs, we're done. What if there is one less than sign? So, M1, and then maybe everyone else is equal. Or we've got two receivers and then three givers. So these are situations where there are no middle people, like we had in A part. So now here we've got two givers. I also wonder, could we make some sort of symmetry argument, like a receiver is someone who just gives -$1. Things to think about. But sort of these are our four possibilities, because there's four places to put the inequality. So these are four cases we could have with the less than sign. Alright, so, well, no reason not to take a look at these. So I've sort of made a total amount of money. I'm calling it 5M. What do we want to do from there? Well, I don't know if I want to call this case 1 and 2 and 3 and 4. I mean, might be a good idea. So for 1, we just have one receiver, 4 givers. So each trade, the 4 givers lose $1. And go down by 1. Now eventually they'll hit the average. So it will take M2 minus M steps for those 4 givers to have $M. And then so will M1. And I guess we could call this case 0. And so then we're in case 0, and we know case 0 works out. So no other assumptions or anything like that. Similarly, step case 4 has 4 receivers. Rather than lose 1 each time on their way up to M. So 4 receivers, they gain $1 per trade. So they're increasing. So they start with M equals, or M1, and it's going to take them M minus M1 steps to get to M dollars. And M5 will have to have, because if 4 of them, you know, this is M, and this is M, and this is M, and this is M, then we've got 4 M dollars, but we know there's a total of 5 M dollars, so it turns out M5 has come all the way down in increments of 4 each time, but has come down to M as well. And so that reduces to case 0, which we know works. Alright, what about these middle cases? And again, there might be some symmetry argument we can make. But it's going to be a little different because we've got 2 receivers, here we've got 2 givers, and so all my receivers are gaining $2 at a time. And so we can't necessarily be sure that we go up by 1 and we're not necessarily going to hit M. So I'm going to say for case 2, and similarly 3, because I really think, and if you wanted to, you could properly phrase this maybe as receivers are just givers who give negative $1 or something like that. That would be perfectly fine. But, you know, we'll say for, and similarly 3. So for 2, what was it? We have 2 receivers. So 2, wait, was it? No, it's 2 receivers, 3 givers. So receivers gain 3 each time per trade. Givers lose 2 each trade because they each have to give $1 to the 2 receivers. Okay, so if we think of M4 is the lowest there and M1 is the lowest here, and our middle ground of M1 is hopping up by 3 each time. M4 is going down by 2 each time. By 2, and then another 3. And then it might happen that they sort of miss each other, and then this turns from case 2 into case 3. Or it might happen that they just both meet M perfectly. So when does that happen? If M4 minus M is even, then we will get to case 0, where everyone has M dollars. If not, otherwise we will eventually swap, and so M4 minus M is odd. So we'll go to case 3. Yeah, we're just going to bounce around between case 3 and case 4. So I guess we could say, let's do something silly. So let's say M was, I don't know, 1. Then we could have 2 receivers both at 0. And then 3 givers, well, that's not going to work. Let's say M is 3. Then we'd have our 3 givers each at 5. Now, so that's step, let's write it this way. So we'll have 0, 0, then 5, 5, 5. And then Each of these will gain 3. Each of these will lose 2. Okay, so that was fine. I need a situation where... So what if the M was 4? And we had... I can't have 7, 7, 7. Let's make the M 5 and 8, 8, 8. No, because that's not going to have the right number of... So, I'm just trying to play around and see if this can happen. What if M is 6? So we have 3 7s. Needs to total up to 30, and then there'll be 9 left over. Well, 9's not even. I question whether this can ever actually happen now. Let's say the M is 7. So that'll be 35. But in order to have 2 receivers, so it looks like you'll have to have M4 minus M is even. So actually, so this is what I'm going to claim. So we claim M4 minus M will be even. So why is that? No, we've got... oh, this shouldn't be M4. This should be M3, because... Just trying to keep my notation the same. I'm picking the lowest number giver and the lowest number receiver to represent the money that all the receivers and all the givers have. So we claim M3 minus M is even, so that you'll definitely reduce down to the all-even case. Okay? If it is even, it's clear that, we just hop down by 2s each time. And so if it's even, you can take, M3 minus M over 2 steps or trades, and you're done. Okay. So, 5M is going to be 2 M1s plus 3 M3s. So 5M minus 3M3 is equal to 2M1. So this will be 2M's plus 3 times M minus M3 is 2M1. And then we can say 3 is M minus M3 is equal to 2 times M1 minus M. I got the order wrong. Well, we'll just swap these two around. There we go. But so 2 divides 3 times M3 minus M. And since 2 is prime, 2 either divides 3, which it doesn't, or 2 divides M3 minus M. Okay, great. You can take a pause for a moment, just breathe. We've done a lot of cases. There's the no less than signs. There's the 1 less than sign. Turns out all of these reduce down to this case. Eventually, the money will all even out. But now comes the tricky part, I think, because we're going to have to start dealing with people who aren't givers or receivers initially, but just like in Part A, might eventually become givers and receivers. So the second sort of situation, if we have 2 less than signs. Remember, the leftmost and rightmost less than signs determine who's a giver and who's a receiver. So we could have them here. You know what? I think I'm just going to make sort of 4 columns. Okay, so we could have, call this guy M1, M2, M3, M4, M5. So we could have a less than here, and then 1 right here, and that would be 3 givers. here and here, here and here, and that would be one giver, one receiver. And that's everything you can have with just one receiver. So now let's talk two receivers and two givers, two receivers and one giver. That's about it. You can have three receivers and one giver, and that's it. So these would be cases, I guess, 5, 6, 7, 8, 9, 10. Now, although it looks like everything's reducing down to even, this is where I think it's going to get hard. And it still might be the case that all you need is the sum of money to be divisible by 5. But maybe, just maybe, there's enough here with some of these non-givers in the midst. The non-givers, non-receivers, sort of non-players, or what did I say? Bystanders. I said bystanders earlier. Some of these bystanders might make it so that some of this step action sort of hops over the M line or something like that, and then we can't ever actually settle down. Okay. So let's have a think about this. Is there one that particularly, I know I've numbered them 5 through 10, but that was just my ordering system. Is there a way to, is there one that I particularly want to look at? Like maybe the one with two receivers and two givers and then one bystander in the middle? Because we're always going to have one bystander for these. Here's two bystanders. Here's three bystanders. Two bystanders, one bystander, and one bystander in M4 there. Alright, so in deciding where exactly we want to go with these, suppose we can point out 10 is similar to 5. Again, the same sort of reasoning of, well, receivers are just givers who give -1. That's a fine argument. So that one's similar, and then 9 is similar to 6. There's one receiver in 6. There's one giver in 9. There's two receivers in 9. There's two givers in 6. Okay. And I think that's it. So 5 similar to 10, 6 similar to 9, 7 and 8 are both sort of symmetric, so I can't reverse them. But I guess we really just have to look at 5, 6, 7, and 8. And in looking at these, I'm not entirely sure which is best to go with. I think I'm going to look at 7 first. And the reason I'm drawn to 7 is just because we have only one receiver and one giver. And so that might be in some way useful. It sort of depends on what's the who's closest. Is M5 closest in value to M4? Is M1 closest in value to M2? But I don't have to deal with any of this 2-step or 3-step sort of stuff that we would or that we have with some of the ones where there's multiple givers and multiple takers. So I think this might be nicer to start off with. I also think 6 wouldn't be bad just because there's one giver and a couple receivers, and that might lead us into 8. Or sorry, not 8, 5. 8 is going to be interesting. Okay? But notice, by the way, that these all have to be equal signs, because I said these are the leftmost and rightmost values now, but the stuff in between here, we don't actually know if all those values are the same. So for 7, I think starting with 7 might be a good idea. Okay, so 7 is M1 is less than M2. I don't know what's going on with M2 to M3 or M3 to M4. And then there's M5. So, the question is, which is sort of smaller? Well, I don't know. Don't want to write that. Let's give a name to these values. So maybe call A M2 minus M1 and call B M5 minus M4, and we really need to know which one's the minimum. I want to know which one's the minimum of A or B. It's a question of what's the best way to write that. So if it's A, then M5 is going to give to M1 so many times that they become equal. So then this case leads to, so after A steps, or A trades, we have M1 is equal to M2. And so, oh, okay, hold on. Let's say it like this. If A is equal to B, then after A steps, or A trades, M1 is equal to M2, M4 is equal to M5. If M2 is less than M3 is less than M4, we'll get something. If M2 is equal to M3 is less than M4, or if M2 is less than M3 is equal to M4, or if they're all equal, well, if they're all equal, that's case 0. If M3 then becomes equal to M4, then we've got, we just have the single less than sign. That's a previous case. Which one was that? So if M3 is equal to M4, so that's 2. Otherwise, and we also have 1 going on here. So this would lead to 2. This would lead to, I think I just said 1 accidentally. It's 3, right? Yeah, 3 is the other way around. Okay, so these are nice. But this other case is going to lead to 8. And we still haven't figured out 8. So we'll have to keep an eye out for that. Okay, but we want to start to think, maybe, well, how can I figure out how 8's going to work? Alright, that's if A and B are equal. If A is less than B, then after A trades, M1 will have caught up to M2, but M4 will still be less than M5. The question is, what is the next leftmost less than sign? Because we could have M1 equal to M4, and so by extension equal to all the ones in between. And then that would be one of the other ones. I think it was 1. I guess we can go back and check. We got the time. No, that'd be 4. 4 was where all the bottom ones are equal. If M1 is equal to M3, then I've got 3 bottom ones that are equal and 1 top one that's not equal, and that's 10, which we'll solve later. And if it's just M1 is equal to M2 is less than M3, then that's 6, right? No, not 6. That's 9, which, again, we'll tackle later by symmetry. Okay, and then if B is less than A, same sort of thing. I almost think you don't need to include this because it's a symmetry thing. But I'll do it just very briefly. After B trades, M1 is still less than M2. M4 is equal to M5. And so again, we have the question, is M2 equal to M5? Because then that's case 1. Is M2 less than M3 but equal to M5? In which case that's one of these other ones. That's 5. Case 5. Or is M3 less than M4? In which case it's just there's 1 lowest one and then 2 highest ones, and that's 6. Okay? So there's nothing to do in 7. There's no choices, nothing to make. It's just a question of, okay, Does it go down to 8, and does 8 also work out? We know 2 and 3 and 0 and 4, these work out, but what about 8, 9, 10, 5, and 6? Okay, but it's kind of nice that these cases are all sort of slowly reducing to themselves. Okay. Well, I suppose we might try 6 next, or 8, get 8 out of the way. I'm not entirely sure. I'll try 8 because it's nice and symmetric. Okay, so case 8, this is the M1 is equal to M2, less than M3, less than M4, equal to M5. And so now, what's going to be happening is 2 givers, 2 receivers, so each of these will go up by 2 each time. Each of these will go down by 2 each time. And again, I think we're sort of going to have this M3 is somewhere, M is somewhere, and these M4 and M5s, they're going to come down by 2 each time. Question is, will they hit M3, or will they hit M, or will they skip in between the 2? I think there's a lot of room for some very interesting things. Okay, again, I'm going to say let A be M3 minus M1, and B be M4 minus M3. Okay, so we ask which one's closest. And I suppose we also ask which one's even, maybe? I'm not entirely sure. Let's say if A is equal to B, then surely they're both evenly spaced around M3. And then that would mean M3 has to sort of be M. So if A is equal to B after A trades, then M1 is equal to M2 is equal to M3 is equal to M4 is equal to M5. Not quite. No, because they divide by 2, I think. I think if A is even, B also should have to be even. Right? Well, let's see. The total is 5M, and that's M1 plus M2 plus M1 plus A plus M1, well, this is actually also an M1, plus M1 plus A plus B plus M1 plus A plus B, again to get up to M5. So this would be 5 M1s plus 3 A's plus 2 B's. No, I can't really see anything that would help me there. This case is not turning out exactly as I had hoped it would. But that's okay. We soldier on. We try and, if I thought that maybe I'm not going to get this case, I might try one of the earlier cases. What I really like is that I have the cases broken down. There aren't too many, I guess, to go through. And I'm making my way through it. So, for example, I know that if there's just one less than sign, I know the game will definitely end. 7, I know how the game's going to play out from 7. It just leads into one of the other cases. So even if I don't get all the cases done, I'm still, I would say, in for some marks. So if A equals B is even, then after A over 2 steps, or trades, or whatever, then we're in case 0. Everyone will be equal. Okay. Now the question is, what do we do if it's odd? A equals B, which is odd. Then after A plus 1 over 2, so one too many steps, M4 is equal to M5, would be less than M3, would be less than M1, which is equal to M2. And so they just sort of bounce around. Now, can I do that? Okay, can I actually concoct a scenario where that is the case? So let's say there are 10. And so let's say M1 and M2 are 1. Let's say M3 is at 4. And that leaves me with, no, not quite enough. Let's say there are 20. Oh, but they also have to be equal. So then they would have to be 7 and 7. Which... No, that works. Okay, so 7 and 7, and it adds up to 20. So what would happen here? So it would be... You get 2, you get 2. And then you would lose 2 to give to each of these. And they just sort of bounce around. Okay, so that's a situation where the game won't end, but it is possible, because I did actually manage to come up with a situation that works and has this problem. So, okay. So that's sort of our first condition where the game with 5 people needs a little bit more to work. So in case 8, we need to have A equals B is even. And how does that affect our case 7? Okay. So I would say C 8 for details as to how you're going to succeed or fail. Okay. Alright. So that's one possibility. Now what if A is less than B is even, then after A over 2 trades, you'll get M1 is equal to M2 is equal to M3, but the M4 and M5 won't have come down enough to meet the M3, and this is another case that we already know how to handle. I want to say it was 3. I almost should write off on the side a little cheat sheet of what all these cases are. Yeah, it's 3. Okay. So we could say similarly, B less than A, B even. So I don't have to rewrite that out. Now, what if the lower of those two is odd? Because then you're going to come up, and then you'll have M3 suddenly becomes less than M1, which is equal to M2, and M4 and M5 haven't come down enough to meet M3. And so either M1 and M2 will have bounced up and also be equal to M3 and M4, or sorry, M4 and M5, or they'll still be less than M4 and M5. This is one of the earlier cases. I'm going to say it was 1. I can't remember exactly. And this was another case. I want to say it was like 5 or something. Or 6. Yeah, it's 6. So this is a case 6. And again, we sort of pass the buck on down the line to, okay, now maybe we should look at 6 or 5. Okay? But we definitely sort of have a situation where things don't work out, and I think that's kind of cool. I think it's kind of interesting. But, I don't know, let's look at 6. So 6 is M1 is less than M2. I have no idea what's going on between M2 and M3. I've got 2 givers and 1 receiver. So it might be a good idea to think of the receiver as sort of taking taking 2 away. So each of these lose 1. So each giver loses 1 per trade. Okay. So again, we sort of get this question of, well, which is the closest bystander? Okay. So again, if B, it's not even that B is less than A, because unlike 8, where everyone's going down the same amount each time, and in 7, everyone's going down the same amount each time, we actually have challenge here. So if A is even, M1 is rushing up by 2s to meet M2. So let's deal just with A is even. If A over 2 is equal to B, then it turns out we'll end up with M1 is equal to M2, and then M3 is equal to M4 is equal to M5 after a while. And so this is either case 0 if they're equal, or it's case 2 if they're not. And we know how the game ends there. Okay. If A is even, but A over 2 is less than B, then that means person 1 gets the same amount of money as person 2 before M4 and M5 take place. So then we're left with M1 is equal to M2. We still have M3 is less than M4, which is equal to M5. And now the question is, do I have an equal sign here? So if M2 is equal to M3, then we're in case 3, I think it was. Don't really remember. If M3 is, if M2 is less than M3, then we're in case 8. Didn't case 8 devolve into case 6, though? It did. So the question is, do we have to now sort of navigate these two, and so that we don't have sort of a recursion or an endless loop or something like that? I think so, but I'm going to put a pin in that for a moment. If A over 2 is greater than B, then M1 doesn't reach M2 in the time it takes M4 and M5 to come down to meet M3 and have the same amount of money as person 3. And so if this is an equal sign, this is case, I think it was 1. If this is a less than sign, this is case, not 7, 5, I think. Yeah. And we haven't dealt with case 5. Okay, so that's if A is even. This 8 and 6 stuff, I feel like this might only get more complicated. Which makes me think that, maybe I should experiment with 8 and 6 before I move on, because I'm so close to dealing with 5, but I get the sense that 5 might also devolve into 6 or 8 or 7 again, and so we might want to take a closer look. Well, while I think about that, let's deal with if A is odd. Or can A be odd? So if A is odd, and B is... If B is less than A plus 1 over 2, then M1 hasn't gone up by 2 and past M2, but we'll still have the M3 equal to the M4 equal to the M5 stuff. So we're good. That's exactly what we just worked out. So again, 1 or case 5. Alright, if, however, b is greater than or equal to a plus 1 over 2, then you'll get m2 is less than m1. You'll get m3 is equal to m4 is equal to m5. And so the crucial question is, m2 and m3, how were they originally related? So if m2 was less than m3, so let's see, m1 might have jumped up, so m1 must be m2 plus 1. If m3 was less than, if m2 was less than m3, then we're now looking either at m2 is less than m1, which is equal to m5, or m2 less than m1 less than m3, in which case this is situation 5, and this is one of the earlier situations. I'll say situation 1, can't remember which one. So that's if that. If, on the other hand, m2 is equal to m5, or it was equal to m3, then what we're really looking at is m2 is equal to m3 is equal to m4 is equal to m5 is less than m1. And again, previous case, I don't remember which one, we'll say it was 4. Okay. So it looks like we don't have a problem with a being odd. But if it's even, we might circle back to this 8 case. So we'll have to take a look at that. All right. I think I'll move on to case 5, and then we'll see what's going on. How many times 6 and 8 are mentioned, or 7, or anything really, because 6 and 8 seem like they're going to go around and around and around with each other. So 5 is m1 is less than m2 is less than m3 equal to m4 equal to m5. Right? Gotta go all the way back. Such a pain. Yes. Okay. So here we go. Alright, so now we've got 1 receiver, 3 givers. Again, each of these lose 1 each time, and this gains 3 each time. So, what can happen? What can happen? Well, I think old standbys of which one's closer, M1 or... is M2 closer to M1, or is M3 closer to M2? But of course, A is being covered by 3's. So if A... If 3 divides A, and A over 3 is equal to B, then they'll all meet in the middle, and that's case 0. I'm just going a little faster because I feel like this is getting repetitive and probably getting boring. I mean, you sort of see where I'm going with all these cases. If A over 3 is less than B, then it'll meet before they meet. M1 is equal to M2 is less than M3 equal to M4 equal to M5. That's a previous case. I don't know, 2 or something like that. If B is less than A3, then you'll get the givers join up with M1 or M2, and that's another previous case. Okay, so nothing bad happens if there's a multiple of 3 in between here. Okay, what if not? If 3 doesn't divide A, well, after... I keep using A plus 1 over 2 just to make an even number, or an integer. Let's talk about A over 3 floor. So that's the number of steps that M1, or a number of times M1 can receive before it gets above M2. So after M1 trades, we still have, after this floor function trades, we still have M1 less than M2. But if we were to round up, we would have M2 is less than M1. And I make a little note of that for whoever is marking. Okay, so now I ask myself, if B is less than or equal to that, then that means these all meet. And once again, we're in case 1. Everybody meets, and M1 is still less than M2. If B is greater than the floor of A3, then we'll have M2 is less than M1. We'll still have M3 is equal to M4 is equal to M5. These won't be equal to M2. So either we're looking at... Either M2 is the bottom of everything, and the 3 that are equal are in the middle. And we'll see if that can happen in a moment. Or M2 is at the bottom, M1 is there, and M1 and M2 have just sort of switched places. And then I think... So this is the same case again, but the numbers are a little closer together. These ones will still be losing 1 each time. This will gain on 3 each time. So is there a way for them to miss each other? Yes, it's entirely possible that they miss like this. Well, if this is indeed possible, so can that happen? Because that's really the last situation I need to look at before I go back and talk about 6 and 8 again. So, can I get all 3 in the middle and the 2 outside are unhappy? And wait, hold on, isn't this this is 7? Right? That was 7. Ugh, now I gotta go all the way back. I'm pretty sure I've dealt with this case. Yeah, that was 7. And we saw that 7 reduced to either 8 or it's 5 and 6 and things like that. So it looks like we're going round again. So this is case 7 or case 5 again. Okay. So what we've got is a roadmap. We understand, given a single case, where it could possibly lead, and we understand the conditions under which it can possibly lead. Now, I would argue that that's probably, worded properly, that's sufficient for all the marks. But, I mean, there's that... We only ran into one problem, and it was right here, where the game wouldn't end. Everything else either goes around and around and around a loop, in which case then it repeats, or it might repeat, or it hits this situation where you stay so in 8 can go to itself multiple times, and so the repeat rule comes into play, and the game stops, but not with everyone having equal. So I wonder if we just need to phrase a little bit. So when does that happen? So it's if A equals B is odd. And we definitely know that this can happen. This is an actual situation that we can have. What if any, what can I say about this, really? And how can I lead this to maybe talking about more of a generic tuple that you start with? Because if I start with just any old tuple, then the question sort of becomes, well, do you know if you're going to hit 8? And do you know if you're going to get exactly this sort of problem with 8? So is there a way to reverse engineer maybe a condition or a couple conditions that we know will cause problems here? Well, I suppose we could take what we know already with sort of a generic one and see where the various cases may be going to fit in. Might be easier to approach it from a starting point rather than trying to work backwards, because I feel like working out the complications between 6 and 8 and 5 and that sort of loop of horror, definitely the less than signs in weird places is causing problems. So I suppose we had something like this. See, the problem is I don't know how many givers and how many receivers. Now, automatically M1 is a receiver, no matter what, because it's going to be the lowest. It's a question of, is M2 also a receiver? And M5 is a giver. So, well, M1 will keep getting things from M5. And he's going to slowly catch up by 1 to M2. Unless they're already equal, in which case M2 minus M1 would be 0. But if there isn't, then M1, if there is, if this is 0, then they're already together, they're already equal. If it's not, then M1 is the only receiver, and M5 will be giving to it. Now the question also, the same sort of thing, is M4 a giver? If M5 minus M4 is 0, then they're both givers. If not, then M5 is the only giver. And it'll be the only giver until it comes all the way down to be with M4. I think there's some symmetry here, so we just sort of need to pick... We need to pick sort of... by symmetry... So who do we prefer? Givers or takers? Doesn't matter. Let's suppose... I don't know. I guess I'm more of a giving person. Oh, no. I don't want that. I want that this difference, if there is such a difference, is less than the M2 minus M1 difference. I think that might be... Because if it's not, then we're going to do the same argument. We're just going to sort of switch the order of things. As I've been saying all along, receivers and givers are not that different. So much so that it probably should have been written down by me at some point. So if that's the case, then... So M5 will agree with M4 first. Now maybe they already do, but if not, it's going to take... He's going down by 1 each time, so it's going to take this many trades for M4 to equal M5. And in that time, M1 hasn't caught up necessarily to M2. I mean, there's this equal sign here. So we'll have M4 will equal to M5. No one can say a thing about M3. No one can say a thing about M2. But M1 will be at something new. I don't know, call it N1. Okay. N1 would be... 5's been the only giver, so it would be M1 plus how many times did M5 give? Well, that's how many trades we've had, and it's traded 1 each time. Okay. So if M5 was already equal to M4, we are 0 trades in, and N1 is equal to M1, I guess is what I'm trying to say. Okay. And we know N1 will still be less than or equal to M2 because I made this assumption here. And if we don't have that assumption, just do the whole argument in reverse coming from the receivers instead of the givers. Okay. So then where do we go? Are the givers going to keep giving until N1 hits M2? Or maybe they've already hit. Maybe they already agree. But from this point on, so this is, I guess this we could say this is after M-5, M-4 trades. From this point on, I know for a fact these two are giving 2 each time. So where do we want to go there? Do we again make the same sort of argument? So I can't make a symmetric argument, sadly. So we're going to have sort of 2 cases. And I know we've already done a lot of case work, and I'm starting to think some of that earlier work was maybe not the best way to go about doing this. Although I feel like I did learn a lot. So let's suppose the difference between M4 and M3. So these are going down by 1 each time. Suppose that difference is less than M2 minus N1, or so N1 will be receiving 2 each time. It'll be closing the gap twice as fast. So should I put a 2 here? Wondering. And then there's the other way. Well, suppose instead, and actually, should this be the equals or should this be the equals? Well, if they're equal, we've dealt with that sort of a situation. Will be in case, not M1, N1 equal to M2, M3 equal to M4 equal to M5. And I've already commented, so a lot of the previous work already commented that this is fine. This will end with all equality, so that ultimately this will go to case 0. But it's these other situations that might be a little different. So I think rather than talking about the difference in terms of A's and B's, I like having these 2's here, and I like actually keeping the M4s and the M3s rather than hiding them behind A and B. So in this first situation, In this first situation, I guess after M4 minus M3 turns, N1 still hasn't quite caught up to M2, unless, we're looking at some 0. No, we're definitely not looking at some 0s. But M3 is equal to M4 is equal to M5. Because the givers have finally brought a new person on board in M3. Right? Yeah, because this less than means that they're only giving 1 each time, so they will come down by 1 each time. Okay? And then, well, it sort of depends on this equal sign here. This was some previous cases. This is either what we called 1, which will end up going to 0, Or this was, I think, 5? And how did 5 play out? Five either went back to itself or ultimately went to 7. And 7 did not play well, as I recall. 7 sometimes went to... 7 went basically everywhere. So what else? What can we do? Unless we missed something with 5, I don't think this approach is helping. Although... we certainly know a lot more. Than... I was gonna say we could... Well, let's think about this. M1, so I'm sort of redoing the M5 case. Or sorry, case 5. So many M's. Gosh, this question's going on for a very long time. So, if these are less thans, which they should be, then what would happen? Well, we said it would end up going to M1, then be M3 equal to M4 equal to M5, less than M2. But of course, this isn't exactly the 7 that we saw earlier, because remember, 7 just said, well, the first thing's less than the second thing, and the fourth thing's less than the fifth thing. We actually have an equality here. So maybe this is a better case to have looked at, because M2, I guess these should be N's, N1s. So M2 gives to N1 until we have 4 or 5 equal, and that's case 0. So this is a bit more precise. We know more information in the middle here. Which, I guess, yeah, we knew more information back here. I just chose to write it off as 7. Yeah, so 5 will keep going to 5 until it hits this, which looks like 7, but there's more information in the middle, and so ultimately we'll go to 0. Okay, so, no, okay, I feel much better than this, about this. So this definitely goes to 0. What if it was the other way around? I suppose I don't even need this stuff anymore. Just copy that same argument with the 7. I should have had that earlier, but I dismissed it too quickly as just, oh, we're recursing again. Alright, now, what if instead we have that it's easier for N1 to meet up with M2 than it is? Then either we'll have N1 is equal to M2, less than or equal to M3, less than or equal to M4, which is equal to M5. Or we'll have so yeah, this is the sort of the only situation that might be causing me a problem. And this might lead back to 8. Well, that's kind of nifty. So this might require a bit more work. Okay, so if instead jumping down by 2s, so jumping up by 2s each time actually causes N to come up then what can we do here? Well, I suppose it's a question of... Because N1 is jumping up by 2's each time. So I think here's where our odd and even arguments that we talked about earlier will come in. So if N1 is increasing by 2, so if we say, you know, let A be this difference, if A is even, then after A over 2 steps, we'll have N1 is equal to M2 less than or equal to M3 less than or equal to, well, strictly greater than, I think, M4. Well, it's got to be, because if those two were the same, they'd be 0, and so this would not have a less than sign. Okay, so we're definitely looking at something like that. Okay. So, if M1 is equal to M3, then this is a situation we've dealt with before. Incidentally, just while I'm thinking about it, we can always replace this N1 with M1, what was it? M1 plus M5 minus M4. Just so that I can start talking about real, original relationships amongst my original quintuple. Because I think that's what we want to go for, is just, you know, pick all the quintuples where this plus this minus this is odd or something like that. Okay, so... now what can we do? Do we talk about M3 minus M2? I think that might be the situation we're in now. So M3 minus M2. If that's 0, we're done. If it's not 0, then that's situation 8. And that is quite specifically... yeah, 8 caused problems only when the difference between them was odd. And 0 is an even number, so I guess, so if this is odd, well, no, it's whichever one's the smallest, because we can also come from above, can't we? So it's if, I guess we can call B the minimum of M3 minus M2, and M4 minus M3. Yeah, because M4 hasn't... well, of course, this isn't the real M4. This is an M4 that has lost a bit. M2 never changed because we haven't added to it, but it's the new M4. Now, M4 has been losing ever since they were equal, and so this is... after M2 minus M1 minus M5 plus M4 over 2 steps, or trades, I guess. So it's M4, and M4 has lost this much. Minus M3. Just trying to put everything all together in a nice big, neat package. So M4 is technically 2 over 2, so we'd be looking at, we have one M4 plus an M1 plus an M5 minus an M2 all over 2 minus M3. And so whichever one of those is odd, so whichever one of those is smallest, if it's odd, then we're done. Then it won't work. So B needs to be even. Okay. So if A is even, then this B needs to be even. And then our game will end. Because then we'll either get 3 of a kind or 5 of a kind. Alright, so now if the A, which is M2 minus M1 minus M5 plus M4, is odd, what happens? So if it's odd, then something passes something else, right? Something goes beyond. So M1 will keep receiving up till a point. So M1 will receive money for A minus 1 over 2 trades, I think. It's been a long question, and I'm starting to lose track of what I'm doing. What did I just do? Okay, so if N1 reaches M2 first, by increasing by 2 each time, then after this many moves, they are equal. Moves, trades, steps, whatever. Alright, so if not, then after... So it will receive 2 each time. After A minus 1 over 2 trades, M1 is equal to M2 minus 1. Because then the next trade, he'll jump over this amount. So M1 is less than M2, but I specifically know where it lies in terms of these things. And we'll still have M3 is strictly less than M4, which is equal to M5. Those two are still givers. They're still giving 2 each time. Alright. So then M1 will go up by 2, and then M2 will be the lowest, and it'll go up by 2, and M1 will be the lowest, and it'll go up by 2. So they'll keep the persons 1 and 2. They were students. Gosh, it's been a while. Yeah, so students. Students 1 and 2 will alternate. The receiver job. Okay. Until when? Until they start approaching M3. Although, what if in the meantime M4 and M5 have come down to M3's level? So I guess different cases. But M3 is odd or even, so eventually either M1 or M2 will catch up to M3, or M4 and M5 will catch up to it. So eventually, so M3 shares a parity with one of M1 and M2. So eventually either one of M1, or I guess it's N1, but I dropped the N's a long time ago. So technically this should be an N, and this should be an N. I don't know why I got rid of them in the first place. I thought because it changed. The heck with it. We'll just call them M1. It's too annoying to bring the N's back in. So eventually either one of M1 or M2 will equal M3, in which case we've got the lowest thing those two are equal and those two are equal, and so either this leads to 0 or this looks like, I think it was 6, except we've got some nice middle information that we didn't have, just like we didn't have the information when 5 turned into 7, or at least I didn't realize it. So eventually either one of M1 or M2 will equal to 3, or we'll have M1 less than M2 less than M3 equal to M4 equal to M5, but we've seen this before. This is case 5, and we like this case because we know this succeeds because we better resolved our 7s. Okay. And so now that I have a bit more information about 6, will it spiral into 8 or what have we got? What have we got? So this is 6, but this is a very special 6 because I know I've got equality in the middle here. Okay. So I was right to look at cases. I was just being too general. I should have started with a tuple first and tried to see what we can do. Okay. Yeah. So M1 will keep gaining 2, but if this is the case, I'm going to put a little star here. Star here. So if this is the case, then we're looking at M2 minus 1 is equal to M1. And that's less than M2 equals to M3. Less than or equal to M4 equal to M5. And it quite specifically has to be less than here as well. Otherwise, we know we're done. Okay. So, what can we do? Or is there anything we can do? It's another sort of odd situation. These ones are back to losing 1 each time. Stuff in the middle. So this will, on the next turn, this will turn to M2 equals to M3 less than M1 less than M4 equal to M5. Because they'll lose 1 each. This will pop up by 2, hop over this because this stays the same. And so now we're back to case 8, which is something we had talked about a little earlier. So the question is, do we get something odd here? Because that definitely will happen once with this situation. So then is M3 minus M1, well, the minimum of M3 minus M1 and M4 minus M1 odd. Well, the minimum would be, because this hops over, so it's just 1. These guys can't be equal, so yes, the minimum is equal to 1. Game won't end. Inequality. So I think we've got it done. The only question is, well, when do I get this specific situation? So that's the last thing to work out. I know when this will happen. This minimum here has to be odd, and this expression here has to be even. Fine. And I know that happens when these happen. Okay, so it's got to be that case. If A is odd, then this and this. Or if A is... So these two combined lead to a solution. This one, as long as A is even and B is even, leads to a solution. And then finally, this case, if the A is odd, and anything except what leads me here. What leads to M1 being less than M2, less than M3? So they eventually one of them will have to equal to M3. That's not what we're worried about. It's so they'll equal to M3 if it's easier for them to get to M3 than M4 is to get to M3. And then, yeah, it'll specifically have to be M4 hasn't met M3. So how do I know M4 hasn't come down to M3? Well, M4 is losing 1 each time. So it takes M4 minus M3 steps for M4 and M5 to come down to the level of where M3 is. But we're saying that, say, M1 or M2 can get there closer, or get there faster. This is the last thing I need, and then I'm done. And then, of course, you would just pretty this up. This is the last sort of condition I need to talk about. So this needs to be greater than something. So the problem is I don't know who's going to... Is it M1 that's going to meet M5? Or sorry, is it M1 that's going to equal M3, or is it M2 that's going to equal M3? That's the problem. So that's the difference between those. So they make those up at sort of twice the regular rate. M5 is coming down to M3, M4 is coming down to 3. They're coming down at the sort of the same value. How can I put this together? So 2M4 minus M3 has to be greater than M1 minus the eventual M2. So just as simple as ending up where they are. So, okay. So we said M5 would come down to meet M4. And that took M5 minus M4 steps. Fine. We were happy with that, and M1 was still less than M2. And then we said, oh, by the way, it's going to take M4 minus M3 steps to come down from there. And we know that this amount has to be greater than M2 minus M1, which is not M1, it was N1, which was its own little monster. M1, M5, and M4. So we know 2m4 minus m3 has to be greater than m2 minus m1 plus m5 minus m4. That's definitely going to have to be the case. So this is m2 minus m1 minus m5 plus m4. But this also needs to be what? Closer than the distance of... Suppose I can bring the M4... I can bring the M5s and the M4s over to the other side. So I'll lose one M4, and then I guess I'll still have two M3s here. So that needs to be true in order to even possibly be in this scenario, but we also need M2 or M1 to get closer to M3 first. And I can't think of an expression for that. Well, let's see. How many steps would it take? So this is the number of steps... No, not this. This is the number of steps it would take for M4 to come down to M3. We know that's got to be that. But we also want... We want to sort of squeeze in the reaching of M3 as well. So how long does it take to reach M3? Well, you're growing by 2 each time. And what different distance are you covering? You have to be covering at least M3 minus M2. So that needs to be snuck in here as well. Well, not M1, it was because I moved everything over to the other side. So I think we're looking at 2m4 minus m3 has to be greater than m2 minus m1 minus m5 plus m4 plus 2 times the distance from m3 to m2. 2 times or a half? It's growing by 2 each time, but you're only covering the distance every other turn, every other trade. So it's like you're effectively growing by 1. Now maybe it's just one of them. Have I got my growth by 2s wrong? No, I'm happy with that. So there we go. I suppose we could bring all the M3s onto one side and something like pull the M4s onto the same side. 4 M3 minus an M2 minus an M1 because the 2 M2s here and this 1 M2 cancel out. So that seems decent, and that's it. So to summarize, I'm not going to write it down because my gosh, I've been going on for a long time. So, to start with any tuple, and we're sort of breaking this down by symmetry, so you can do sort of the opposite sort of thing, or the opposite equations, just flip around all the M1s change to M5s, and all the M4s change to M2s, and the M3s stay the way they are. But if it's a closer distance for M5 to reach M4, they might even already have been there. That's fine, so that's the assumption we've made. Now, both of these situations will be fine. If, however, 2 times M4 minus M5 is greater than M2 minus this thing here, which is M1, minus M1 minus M5 plus M4. I guess I could have brought the M4 over to this side as well. Then you can still succeed. So really what you're trying to avoid is having this value here, or this expression. So it might be easier to say when we can't end the game, and then everything else works. So everything works unless you have this situation, this thing is odd, as well as the minimum of these two values is odd. Alternatively, if you've got this inequality, and you have, it's easier for M1 or M2 to agree with M3 than it is for the M3 and M5 and M4 to come down to M3, then that will also, that will also cause a problem. Anything else is fair game, and I think at long last I'm done with this question. I did not like this question at all. But that's, that's how it goes. Sometimes you like a question, sometimes you do not. Okay? But I'd say definitely the casework I did much earlier in the video would definitely count for something. But I like at the end, sort of, I stumbled upon more of a approach it head on. So just start with a generic tuple and see what you can do. But of course, this latter part went a little faster because I'd already done all that casework. Anyway, that finishes off the 2015 COMC. Otherwise, a great paper, but I know I definitely did not like C4, and I think it came across towards the end. I was getting fed up there. Okay, but up next will be the 2016 paper, so I'll see you for that then.